All right, so I'm Fabrice Drouin. I work at Async, and we're one of the teams working on designing and implementing Lightning. And today the presentation is going to be about the technical choices we made for our own implementation of Lightning. And it's for the residents, it's going to be on the lighter side. It's not going to be as heavy as the stuff you've been bombarded with for like 2 days. It's going to be a bit more fun. I'm going to explain why we chose the tools that we are using and why we think it was a good choice, obviously. So, who doesn't know what Lightning is? Okay, so I'm going to give you. So I'm going to go really quickly on this. It's a payment system that is built on top of Bitcoin, and it's a very special project because I think it's unique in that it has an open specification that anyone can look and try to implement. I don't think there's anything like this in the cryptosphere. So basically, what you have today is a specification that is quite complete. It's low level, but it's quite complete. You have 3 major implementations of Lightning that you can use and that are interoperable with each other, and you have new implementations being developed. There's a Japanese team, Nayuta, that has a C++ implementation. Electrum is working on a Python one. There's Lit at MIT, also in Golang, I think. Go. So what you have today is a spec that is at 1.0 that covers all the things you need to implement to run a Lightning node and connect to the network. So it covers the binary format for messages, the Bitcoin transactions, the discovery mechanism, the gossip messages we exchange to learn about the network, and how to design payment requests for Lightning. So as I said, the major implementations are C Lightning in C, Eclair in Scala, LND in Go, and you also have Ptarmigan and Rust. I think someone here is working on the Rust implementation, and others coming in Python. And what we chose is Scala, and it's not a very popular framework. Who knows what Scala is? Good. Who has already written Scala code? Okay, it's like 3 guys out of maybe 40 or 50. So it's not a very popular framework, but we still think it was a good choice, and I will explain why we think it's a good choice. So when you think, I want you to try to picture C developers, Go developers, and Scala developers. Get a mental idea of what these guys are supposed to look like. And when you think of C, basically that's what you think of. The C guys, like bearded old guys, they know everything. They can. Okay, that's C developers for you. If you think of Golang and Rust, this is probably what you have in mind. It's like they're the cool kids, and I would say that in cryptocurrencies, Rust is even cooler than Golang, slightly cooler than Golang. Rust is cool. And Scala, well, nobody knows what Scala is. So very often when I have to explain what Scala is, I say it runs on the JVM. And this happens. And it's not how it works. And Scala really is an awesome platform, and I'll try to explain why. So Lightning, basically, it's a peer-to-peer network of payment channels. And a payment channel is something that maintains unpublished transactions and updates unpublished transactions. And we try to do this in a way that is trustless. So you open Lightning channels by publishing a funding transaction to the blockchain. And then all the trick is to send messages, to exchange messages, to update what we call a commitment transaction that spends that funding transaction and without having to publish it. So basically, you can think of the funding transactions as an account that's as a joint account, and the way the money is split in the joint account is reflected in the commitment transaction that we update to shift how the money is spread. So what you have are nodes that are connected to each other over TCP and that exchange messages to update their commitment transaction. And the payment model we have in Lightning is HTLC, hash time lot contracts, where basically you pay for the pre-image of a hash, and if after some time you haven't received anything back, you get your money back. So this is what Lightning looks like. I guess everybody knows. You publish your funding transaction, you have your commitment transaction, you update it. So it's a 10 Bitcoins channel. Basically, you're moving money inside that channel from Alice to Bob. You can do that as many times as you want. It's not touching the blockchain. And when you're happy, you can close the channel and publish the current state of your balances back to the Bitcoin blockchain. So on Bitcoin, you will see the first and last transaction, but it could be 1 million updates in between that the blockchain would never see. And that's the structure of the commitment transaction. You don't really need to dive into the details, but basically, in a commit transaction, you have an output for you, an output for your peer, and one output for each pending payments, each pending HTLC. And these outputs will be resolved, will be removed, either when the payment has failed or when the payment has been completed and you've received the pre-image that matches the payment hash. So Lightning is a network of such Lightning channels. So each node on Lightning has a node ID, it's a public key, it has the matching private key, and connections between peers are encrypted and authenticated. And channels are multiplexed over one single connection. So you have one single TCP connection to your peers, but you can have many channels that are multiplexed over that single connection. And the protocol we use in Lightning is a batch protocol. You can send many updates, and you sign the updates, and you commit all the updates to the commitment transaction. So in this case, A and B have exchanged new payments, and when A signs, it will commit to the payments it has sent, and B will send an acknowledgement, which means it knows of these. You can assume it knows of these payments because we assume that messages are ordered. So if you send a revocation, it means you've seen the signatures that were sent, which means you've seen the messages that were sent before the signature. Nodes, basically the job of a node from a functional point of view is to maintain two commitment transactions, your local view of the channel and the remote view of the channel. And they are different. They're never the same because A can send updates, B can send updates at the same time, and B and A will not necessarily sign the same view of the network. So basically your job as a Lightning node is to maintain a consistent view of your commitment transaction, the other guy's commitment transaction, and make sure that they match. So from a functional point of view, a Lightning channel is a state machine. Every time you receive a message, you will transition to a new updated state, and optionally, and in most cases, you will send back a message. You need to maintain origin and destination information for what payments you've relayed. So if someone tells you to relay a payment, you need to know what the upstream channel was, what the downstream channel was, and when you receive the pre-image on the downstream channel, you have to remember where to send it back on the upstream channel. So you have to maintain associations between upstream and downstream channels. So in a nutshell, the design constraint you have if you want to implement a Lightning node is you're building a server application, something that will be running like for a long time. You have to manage TCP connections. You have to pipe incoming messages to channel state machines, and you have to pipe the message back to the outgoing peers, TCP connections. You need good cryptographic libraries. Mostly you need a really good SecP 256K1 library. And you need good beacon libraries, obviously. And you get bonus points if you have good performance from a CPU and memory point of view. You need good tools to build and deploy and debug what you're doing. You need to be able to understand what's going on. You need to have some kind of monitoring that is built in what you're using. And as much as possible, you want something that you can run on different operating systems. And you need to have a vision of what you want to achieve. That's very important. Our goal was always from the beginning to build something that we can run on servers and manage fairly large nodes, lots of channels, lots of payments without having to spend too much time babysitting that thing. For a very long time, there were 3 of us with the mobile application, the servers, Strike, other things. So we wanted to have something that would basically you would start somewhere on Amazon somewhere and then just forget about it. And you would come back and check that everything was fine, but basically something that has almost no maintenance. That was very important for us. So with our vision of what we wanted to build, what we needed was a really good runtime, something that was efficient, something that gave you monitoring facilities, something that was possible. We needed a good programming language. And good programming language means expressive and readable. And readable means that when you look at the code, you understand what the code is doing, and you also understand, and it's even more important, what the code is supposed to be doing. For example, if you use really low-level languages, it's very easy to see what the code is doing. It's not always very easy to see what it's supposed to be doing, what the intent behind the code was. If you use high-level languages, you have the opposite problem. It's easy to understand the big picture, but what is actually happening? Sometimes when it comes to low-level threading issues or memory issues, how memory is managed, sometimes it's a bit difficult to understand. So we wanted something that was readable and that would also convey intent, what we were actually trying to do, and just not the code. And we needed good libraries, good primitives, logging libraries, and a very good concurrency model. In Lightning, that's very important. That's the way you implement concurrency is very efficient. You don't want to have concurrency bugs. You want to be chasing what was going on between your different channels and your peers and your connections. So these were the most important criteria, in our opinion: the runtime, the programming language, and the concurrency model. And for the runtime, we chose the JVM. So the JVM is probably one of the most underrated runtimes today. Everybody thinks it's not that good because I must admit that most people have a really bad opinion of Java. But the JVM is really awesome. It does a lot of things very efficiently. It has really good memory management. And it's fairly fast, much faster than what people think. I'll get back to this. And the language and tools we use are mostly Scala and Akka. Who has heard of Akka? Okay, Akka is an amazing concurrency tool, and I will explain how it works later. So JVM, as I said, I believe is one of the most performant, reliable, and underrated runtimes you can think of. It actually runs everywhere from mobile devices to really large servers. It has what I think is probably the best garbage collection and memory management you can find today. It's really efficient. It uses garbage collection, so you don't explicitly deallocate memory. And there are many ways to implement this. The simplest and least efficient way is just stop the world. You stop everything, you compact memory, and you start everything again. This is really, really bad, and Java has today different options that are way more efficient at this. Basically, if you're careful, garbage collection never gets in the way. You don't see you don't see the impact on your performance if you're careful. It has very good performance. If you use naive, basic, simple implementations of algorithms, you will see that Java code or Scala code is often almost on par with non-optimized native, as in C or Rust code. Usually, if you take an algorithm and you implement it the way it's like described on Wikipedia, the difference between your code in Java and your code in C is going to be maybe 10, 15%, not more. It's going to be 5 times faster in C. Because Java uses what is called just-in-time compiling, basically the name of the virtual machine is hotspots. Hotspots mean it looks at what's going on, and when it sees something that is heavily used, it will compile it to native code, which is why everything that runs on a JVM needs to warm up. It's going to be slow at first, and it's going to get faster and faster as the application runs. But in some cases, it can be too slow. When I say that performance is on par with non-optimized native code, if you get a domain expert to optimize your code, a domain expert who knows exactly what your algorithm is supposed to be doing and who has a good understanding of your target runtimes, then native code can become much, much quicker than Java code, and much quicker. Like the best example we have is SecP 256K1. It's about at least 50 times faster than all the Java libraries you can find on a JVM. 50 times is a lot. The good news is it's very easy to call native code from Java code. And this is what we're doing. We package native libraries into our Java archive. So if you run Eclair, you use native bindings for SecP 256K1. You don't even need to think about it. And the bonus point is it runs also on Android. And the really good thing about the JVM is when you want to profile your application or debug your application, you profile the JVM, not your code. That's a huge difference. Very often, if you want to profile or debug, you change your code. You instrument your code, which means that what is running in the version of the application you want to profile or debug is not what is running in production. The JVM is very different. The bytecode is the same. It's just you ask the JVM to give you more information about what is going on. And this is really nice. You can learn a lot of things. You can see what's happening, how the CPU is used, how memory is used, how garbage collection is used. It can tell you information on, okay, you have too many short-lived small objects. You can really learn a lot, and you do this with your actual production application. You don't need to change the application. It's like it's not the Heisenberg principle. You're not changing the thing you want to observe. And there's something that is really nice about the JVM. It's not just about Java. It's used on billions of devices, and you have many different programming languages you can use on the JVM. You have Java, obviously, Scala, Clojure, Groovy, Kotlin. You can run Python and Ruby on the JVM. Some people do. It's extremely stable. It's fairly hard to crash the JVM. It's really hard, unless you run out of memory, but nothing will survive this. Basically, it just doesn't crash. And the good thing about JVM is if you use a language that targets a JVM, you can use any Java library. And popular Java libraries have millions of users. Millions. So you don't have to worry about your network stack or whatever library you use. It's really heavily used. And it has really great tooling. You have build tools, dependency management tools, development environments, monitoring tools, debugging, deployment things. You have everything you want for free because these tools are built for the JVM. Scala. So Scala is like a mixture of object-oriented and functional programming. It has good side and bad side, and someone I like very much said it can be used as a better Java or as a worse Haskell. And that's very true, and that's one of the problems with Scala. But it comes with lots of goodies. You have pattern matching, case classes, like data classes you see in Kotlin. Immutability, by default, everything is immutable. This, coupled with a good concurrency framework, means that you don't have to worry about what is happening to a value when you're debugging. It's not going to change from under you because it's being accessed by another thread somewhere. It changes everything when you want to debug things. You have an option type that means you don't need to worry about null values. And you have futures, which are really good for abstracting asynchronous events. It's extremely expressive. So typically, if you port a Java application to Scala, you will have between 5 and 10 times less code. But it's still readable if you are careful. Again, readable means you can tell what the code is doing, but you can also tell what it's supposed to be doing. It's not always true, and one of the huge problem with Scala is that there are many ways to do the same thing, and if you don't have discipline, it scales pretty badly with the size of your team. So if you can have many different styles of programming, and if you let people choose how they implement things, after a while your code is a mess. Sometimes it looks like Haskell, sometimes it looks like C or C++. So you need to be extremely strict when it comes to discipline and consistency. And we are very strict. We're still a small team now, and if you open a pull request with us, we'd probably ask you to rewrite a few things before it gets accepted, because we think that consistency is extremely important. So we won't let you get wild with Scala Z or whatever. You have to follow what we've been doing so far. If you do that, I believe that Scala is extremely readable. And the really good thing about Scala and Akka is the actor model. So who knows what the actor model is? Okay, so traditional concurrency is dealt with shared state and locks. So basically, you protect the states that a lot of threads will try to modify with locks. It leads to contention issues, sometimes deadlock issues, and it's very hard, as in impossible to debug. You stop the debugger somewhere and you have, basically you change how your program behaves, and the things you were supposed to diagnose doesn't happen, or not in the same way, because you've stopped something. The actor model is completely different. Basically, state is never ever shared. And instead, you have entities which are actors, and they communicate with each other through asynchronous message passing. So actors send messages to other actors. Messages are processed one at a time, and the actor will send back a reply, which could reflect some of its state at the time it received the message, but state is never ever shared. And the actor model is extremely easy to reason with. It's not a generic solution to all problems, but if you want to implement state machines, it's very, very nice, because your actor is your state. You receive messages, you process messages sequentially, you emit a response, or you transition to a new state, and you don't need to worry about concurrency. So Akka started as a port of Erlang OTP. Who knows what Erlang is? Okay, more people than Scala, actually. It's a language that was designed by Ericsson for telecom software, and that's supposed to be extremely resilient. And it includes the actor model and other things like supervision trees and everything. And Akka started as a port of Erlang actors for Scala. So it includes actors, finite state machines, TCP and HTTP clients and servers, logging frameworks, configuration, remoting, and Scala is awesome. If you have not tried Scala, I would say that Akka is a good enough reason to give it a try. It is really awesome. So if you've never seen what it looks like, this is a very basic actor that receives messages to set, add, or subtract values from its state. And you can see what I meant, hopefully, by readable. I think even if you don't know Scala, if you don't know Akka, it's fairly easy to understand what the thing on the left is doing. And the really good thing is that you don't see the framework. There is no notion of concurrency here. And that's what is really good with the actor model, and the way it's implemented with Akka is you don't fight the framework, you don't see it. It's not there. What it does is not something you have to worry about when you are actually implementing your code. There's There are no locks, no queues, no nothing. All you see is you receive a message, you update your states, and eventually you send back an answer. So it's very nice in that way that you don't fight the framework. And there are no locks. That's very important. So we designed Eclair as a system of actors. There's one for handling the TCP connections between all your peers. There's one for computing routes. There's one for dealing with a transport layer that is encrypted and authenticated. And there's one for dealing with payments. And all these are actors, and all they do is send messages to each other. There is no shared state anywhere. So if you look at one of these entities, again, it's fairly easy to reason about what it's doing and what it's supposed to be doing. So in production, again, our goal was basically selfish. What we built is what we want to run in production ourselves. Every decision we take on the technical issues is it good for running our node in production? So that's our main focus. Most of you will probably know the mobile application, but actually 95% of our time is spent working on Eclair, which shares a lot of functionalities with the mobile application. And our target is always, is it good for running the thing in production and not having to worry about it crashing or stopping or whatever? And today, on one single server on Amazon, we have a fairly large and busy node with hundreds of peers, thousands of channels, and lots of short-lived connections from mobile application. You start your mobile phone, you use it, and you turn the application off after a few minutes. So it's quite demanding on the server side. It runs on a single machine, and it just runs. We haven't had a database corruption ever. And until a few weeks ago, it had never crashed once in 18 months of really heavy use in production. So it just doesn't crash. I was through until I think 4 weeks ago, and a few weeks ago we started to optimize things. So we never optimized anything. We implemented things as simply as we could. And a few weeks ago we started to see that, okay, the garbage collection pattern was not too nice. The CPU usage was not too nice. Again, it happens when you have really lots of peers, lots of channels, and lots of payments. And we decided, okay, maybe we could improve this. And one of the optimizations was actually not too good, and it didn't really crash, but it stopped working, which is more or less the same. We had to kill it and roll back the changes. But until a few weeks ago, it had never crashed once in 18 months in production. And it's extremely easy to understand what's going on. Basically, the way the logs are structured, also that's something we're very, very annoying with. If you submit a pull request, we're going to ask you to check your logs and make sure that you follow the patterns that we've implemented, so that it's easy to understand what's going on by just looking at the logs. So it's something that basically we were able to run just the three of us for a very long time without having to actually try hard at understanding what was going on. Even though now there's 6 of us, almost everything was done by 2 developers for a very long time. So I would say that, again, it's our opinion for the specific target we have, which is, again, have a node that runs somewhere in the cloud and that you don't have to worry about. The JVM, it is really a good runtime, and it's better than you think, because you all think it's not that good. Scala as an expressive and powerful language. Eclair today is 22,000 lines of code. It's much, much less than LND or C Lightning or Electrum or whatever, much less. Because it's expressive and it's still readable. And we have an awesome concurrency model and actor library. We never had a concurrency bug or a performance issue or memory issue that was caused by Akka. Akka is awesome. And the good thing about Akka, it's extremely easy to reason about what's going on. It really doesn't get in the way. So even though I would say that even though I don't develop Lightning nodes very often, when I do it in Scala because it's awesome. And that's the end of it.